Good afternoon, everyone. Welcome to today's webinar, which is titled IEEE 1584-2002 Arc Flash Study, Good Enough for a Post-IEEE 1584-2018 Risk Assessment. My name is Mike Eby, Group Editorial Director with EC&M, and I'm going to serve as the moderator for today's event. Before we get started, I need to run through a few housekeeping items. This webinar platform allows you to watch the event the way you want to watch it. So in other words, you can customize the console to your liking. You can move windows around by dragging on the title bar, or you can resize the windows by clicking on the lower right of any of the window boxes. There's also a toolbar at the bottom of your console, and these buttons allow you to open and close various widgets on your screen. If at any time you have difficulties with audio or the slides don't seem to be advancing, just hit your F5 key and it'll refresh the console. That should clear up any problems you're having. We also encourage you to ask questions at any time during the session today using the Q&A widget, which is on the left side of your screen. We'll address as many questions as possible at the end of the presentation. And lastly, please be sure to share your thoughts with us today by clicking on the survey icon and completing the form. Now it's my pleasure to introduce today's presenter. After more than 41 years with GE, Marcelo Valdez joined ABB Electrical Products Division in July of 2018. He's held various positions over the years in field engineering, equipment sales, application engineering, and product marketing. He's the past chair of various IEEE PES and IAS chapters in North California, as well as past chair of the 2014 IEEE Electrical Safety Workshop. He also chaired IEEE 1683 2014 Working Group, which was focused on low-voltage motor control centers, and is active in various other IEEE working groups, mostly in the electrical safety and electrical systems protection areas. He's received multiple recognitions from various IEEE areas in overcurrent protection and electrical safety. He received the IEEE IAS Applications Magazine First Prize Article Award for a 2014 article on assessing solutions to electrical hazards, an analytical tool to reduce hazards in electrical facilities. He's authored or co-authored more than 35 technical papers for IEEE and other engineering forums. And he participates in Canadian Electrical Standard, CSA Z462, NEC, NFPA 70B, and other standards. He also holds 28 patents in the field of electrical distribution and control. So with that, that's now my time to turn it over to Marcelo and let him get started with today's presentation.
Hello, everybody. I hope you can all hear me well. I hope everybody's staying safe in these difficult times, doing what you need to do. Not an easy thing, but this too shall pass. This presentation is based on a paper that I presented at IEEE Electrical Safety Workshop this past March, probably one of the last IEEE conferences held before things started shutting down in the US. One might ask, why this subject? As was mentioned in the introduction, I've worked with a lot of IEEE electrical safety groups. I was part of IEEE 1584 working group and other related organizations, committees, etc. One of the questions that I have gotten multiple times from multiple people is, now that there is a 1584-2018 that has replaced the 2002 version of 1584, what do I do with my old arc flash study? What do I do with my old PPE selections? And since NFPA 70E gives you several years to redo your studies based on whether, and then redoing it based on whether your electrical system has changed or not changed, etc., can I just continue using my 2002 study, my 2002 PPE selections, till I get around to doing the 2018 risk assessment? Very common question. I'm not sure that I have a clear answer for that question. Let me figure out how to move this. Okay. The answer to that question to a great degree is is a legal answer, and I'm not a lawyer, much less a labor lawyer or liability lawyer or safety lawyer that can truly answer that question from the legal perspective. But I do know that an arc flash study is essentially a tool to give you a data point to be used in risk assessment and risk control. So at the end of the day, 1584 to 218 is a change in the arc flash science. Think of it that we thought the world was flat. Now we think now we kind of know the world is round. Should we be doing anything any different? Well, the answer to that probably is yes. So the question is this a legal issue? Perhaps, probably, in fact. Is it a safety matter? Well, definitely, because the results from a 218 calculation compared to a 2002 calculation can be very, very different in both directions, not just greater hazard. In some cases, it's less hazard. But primarily, this becomes a risk analysis question. When you go do a task and all the data that you have is the data from 2002 study, how should that influence your risk analysis? What else might you do? And that is essentially the reason for this paper. From the perspective that, according to Mr. David Michaels, a past Assistant Secretary of OSHA, is that this is all about managing and controlling risks in the workplace for workers and to make sure that people are doing the best they can to mitigate the potential of serious injury and illness to workers in the workplace. When we look at risk management in 70E, it talks about monitoring and reviewing risks. I think that's an important concept. A risk assessment, which is part of risk management, involves analyzing risk sources to estimate risk level. Risk level includes the potential for a dangerous event, the potential severity of that dangerous event, and the two need to be sort of looked at together. And from that, you evaluate whether you need to do something about that risk, to control it, to treat that risk. It tells you, furthermore, that risk analysis needs to be systematic, structured, and timely. Then you need to use the best available information. And I think somebody were to push you and say, well, I used the 2002 1584 method versus the 2018, and it's now 2020, I'm not quite sure how easy it would be to defend the position that you use the best possible information when you use the old method versus the new method. It tells you that risk analysis has to be dynamic, iterative, and responsive to change. Again, the way you calculate the science has actually changed. Okay, so what are the changes? There's several. Probably the single most important one is that in the old model, all the tests, all the data that was used to create the model was based on the conductors that caused the arc flash, that held the arc, being parallel to the worker. The term used in the documents is vertical, but in reality what it means is that the bus bars, cables, the source of the electrical energy is parallel to the worker, i.e. it's kind of like looking at a train that's going by you. Now somebody could throw something out the window of that train and hit you, and the speed of the train, how much stuff they throw at you will have impact, but the train is not going to hit you because it's going by you. Now in the new standard, there is a so-called horizontal perpendicular electrical orientation. Now think of this, now the train is going to hit you. It doesn't take a lot of thinking to realize that's kind of worse than if they throw something at you from the train. Another condition considered in the new method is the so-called vertical, parallel, into a barrier, i.e. the train is going by you, but it's crashing right in front of you. More serious than just going by you, maybe less serious than going straight at you, but pretty serious. Because it is going fast, it's a lot of mass, and it just crashed in front of you. So to sort of simplify the example, I'm using this analogy, that those two conditions are fairly different from what the previous standard was. As far as voltage, gaps, even enclosure, the new method is very similar. Enclosure is a variable for energy, not for arcing current. The gap is now allows for more continuous measurement of the gap. So if you previously used a certain value and now you want to use a 10% larger value for whatever reason, you can, and it will have an impact. But in my experience, talking to people that do studies, I find that most people tend to stick to the values that are in the tables in the IEEE guide, and those values have not changed, the so-called 13, 25, 32, and 40 millimeters. Most people, for low voltage, most people tend to use those values. In reality, the new model allows you to use different values, unless somebody's taking a tape measure or knows what those values are. It is improbable that they're changing them for the arc flash study. They may, and some of you who are in the business of arc flash study may contradict me, and because you guys are following a more thorough or more detailed process than the people that I have seen. But the main issue is the arc pointing at the worker or not? Is that electrical conductor a rail gun for the plasma? Is the arc constrained or free? Is it an itty-bitty little arc or a great big one? And most of those variables are kind of in the old model as well. The new model is a little bit more accurate. I mean, we sort of imply or believe, have a fundamental belief that the new model is more accurate. It is based on a couple thousand tests, whereas the old model was based on a couple hundred. So there's significantly more data. It was done a little bit more scientifically with the multiple variables. Overall, the consensus is that the new model is more accurate than the old model. The equations for all this are actually quite complex, or complex looking. When you come to programming this, like in Excel, actually, it's not that complicated, and it's quite doable. But there are a lot of equations, a lot of steps, a lot of logic in deciding what you do, when, and how. And that's not something that is typically accessible to the typical worker. If you have an arc flash study, all that is done by your software. If you have an Excel spreadsheet that does this for you, it's all done by the calculations Excel spreadsheet. But typically speaking, your average worker who's looking at risk for a task either had this done to him and handed to him, put on the arc flash label, or it's out of his access. If you look at a 2002 study, you look at the system voltage, fault current, arcing gap that develops the arcing current. You take that arcing current, you plot it on a time current curve that develops time. You may be doing some elements of risk analysis to figure out, well, can I trust that time current curve? Can I not trust it? Do I need to add tolerance? Am I using the right device? There is some risk analysis that probably should be done there. Similarly, do I have multiple topologies, i.e., do I consider this with motors on, motors off, the emergency generator connected, emergency generator not connected, etc. All kind of goes into that risk analysis when you're calculating current, which time current do you use, etc. And that develops a time. That time is then used again with the system voltage, fault current, arcing gap, blah, 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 to develop energy. Now you have an incident energy number. Again, you go through a risk analysis process and you develop a recommendation for PPE, typically higher than the incident energy that you've calculated. But again, in the old study, there was only one electrode configuration, one electrode environment. In the new method, you'll have to add that as a variable. And that ends up being a big variable. Box size is also a variable in the energy calculation. And again, in my experience, most people are not fooling around with that variable, and they're kind of using the suggested values, the standard values, most of the time. Not saying that that's wrong or right. That simply seems to be what most people are doing. Me personally, I think I have an issue when the boxes are very, very, very big, and what that does to arcing current. Well, that's a different conversation for another day. The net issue here is that your big impacting variable is that electric orientation, which impacts both arcing current, seen on the left here, and the incident energy seen on the right. Excuse me, the arcing current seen on the left and the incident energy seen on the right. That horizontal, vertical, or vertical with a barrier impacts both of those calculations. So we know that the electric orientation is a very big and important factor. The good thing is that that's a factor that can be decided upon by a simple physical inspection of the equipment, of the conductors, of whatever the exposed conductors that you think could have an arc flash. All you have to do is look at them, look at the direction of the power going into the potential arc. Is it horizontal? Is it vertical? Is it going to run into a barrier and sort of crash into something, or is it going to just flow fairly easily? And that can be done by inspection. You don't need a PhD in obscure sciences to figure that out. So other factors such as the gap between conductors probably is not going to change when you do a study, again, unless people are trying to be very, very exact and they have some exact measurements. Most people will use the so-called recommended or suggested values, typical values in the tables within the guide. And that's a 13, 50, 25, 32, and 40 millimeter numbers that we're familiar with. If the gap happens to be smaller, it actually doesn't matter because it will give you a higher arcing current and less energy, both of which turn out to be conservative variations. If you know the gap is going to be a lot larger, that kind of throws a wrench in the works because now you get less arcing current, harder to detect, and B, you get more energy per unit time, potentially a more hazardous situation. The method I'm going to discuss does not deal with that possibility. It assumes that the gap is going to be the same or smaller. If you are doing an arc flash study, a little side point, and you're not sure about the gap, use a larger number. Using a larger number always is the conservative thing to do. Again, we can discuss that in details at a different time. Let's look at arcing current difference between the old study and a new study for the similar conditions. There is a characteristics of the two that is very important and actually sort of facilitates the process I'm going to describe. And the fact is that generally speaking, in the new model, for a VCB, HCB, or VCBB, i.e. vertical electrode, horizontal electrode, or vertical electrodes into a barrier, the arcing current will be higher than what the old study would have predicted. That's a horizontal, that IBF at the bottom there, and you look at the arcing current as the vertical axis, you'll see that those colored lines are generally above the black line. Those color lines are curved, they have a little belly to them, they're convex, and the black line is kind of a straight line. And for most of the range of current, the color lines are above the black line. Notice that to the right, where I have the little red egg, that's no longer true. For some scenarios, the arcing current in the new model will become lower. But when you look at the range of IBF, you'll see that that tends to be for very high bolted fault currents, 85 Ka, 75 Ka, 90 Ka, 100 Ka, values that we don't typically run into in real-world systems. Most real-world systems tend to be 55 Ka and below. 50 to 20 Ka, 50 to 15 Ka, you're dealing with panel boards, motor control centers, switchboard, switchgear, and your typical industrial commercial facilities. If you're downtown New York City, completely different kind of worms, because there you have 200 Ka systems. To tell you the truth, you shouldn't be doing energized work in those situations, period, end of discussion. not addressing here. I'm trying to address your more typical industrial commercial systems where your gear is rated 65 kA or below, and you're dealing with those more reasonable typical currents. In that IBF range, arcing current typically in the new study will be higher than in the old study. That's a good thing. Makes it easier to detect. Here's another calculation, in this case at 208 volts, 25 millimeter gap, standard low voltage box. Again, your arcing currents typically are higher, but notice how they flatten out, which means that if you are calculating an arc flash for very high fault current systems, now you have a different scenario where your protection may act very differently than you expected it to, and you may get some widely different results. But in this middle range, it kind of holds true for almost all voltages, all gaps. The new study will give you a higher arcing current than the old study. When you look at protective devices, whether they're circuit breakers, which are shown by that orange curve, or a fuse, which I sort of simplified and grouped together with this black line here, typically an I to the fourth characteristics, and you compare with that red line, which is called a constant energy boundary. Notice that this is arcing current. You'll see that the circuit breaker overcurrent element, the fuse overcurrent element, are both steeper than this red line. What does that mean? That means that if you only know one thing about the 2018 study versus the 2002 study, and that is that the arcing current is higher, then what you do know is that your protection is going to be faster, or if your protection hits these horizontal portions in the circuit breaker, it's going to be the same speed. What you do know is that it will never be slower. Your protection is going to be the same or faster every single time per the studies when you compare the 2002 versus the 2018. So without looking at the time current curve, without knowing what the exact arcing current value is, you know your protection is going to clear at the same time or faster, never slower. And that's an important little fact here we're going to use. When you look at incident energy, the comparisons are not quite so clear. Here you have 480 volts, 32 millimeter gap, standard box, 18 inches, 100 milliseconds clearing time, being fixed for all these conditions. And you look at the dashed line, which is a 2002 study. The color lines are a 2018 study. The VCB gives you less energy per any particular value of voltage fault current. That's a good thing. Means that the old study was conservative. For a VCB situation, it kind of depends on where the fault current is. Again, kind of in this middle range, the VCB may give you more energy than the old study. For HCB, kind of all bets are off. It's pretty much all the time will give you more energy. Here we're looking at 208 volts, 25 millimeter gap, 18 inches, 100 milliseconds. Kind of the same, but notice at the top here, the HCB is actually less than the old study would have given you. This area where VCBB is smaller than it was in this graph. VCB, again, is consistently below. So the energy comparison is a little bit more complex. It's what it comes down to. And if you go to look at the impact of gap, you'll see that there is a small change in arcing current. There is a small change in energy. And here you'll see the green curves are in the bottom. Here you see the green curves are on the top, which making the gap smaller, conservative. Making the gap larger makes things more difficult. Increases energy, lowers arcing current, makes things more difficult to detect, and makes the energy per unit time higher. So a larger gap, if you look at your old study and now you try to properly do a new analysis, you realize, oh, I should have used a larger gap. That's a more complicated situation, and that's not what we're trying to address here. We're making the assumption that the gap is going to stay the same. But the big difference here is time. 50 milliseconds, 100 milliseconds, 200 milliseconds, same conditions, VCB, 32 millimeters, 18 inches. Huge difference in energy because time ends up being an important factor, very important factor. There's a tool that people that deal with arc flash sometimes use for analysis, particularly when you don't have exact values of voltage fault current. And that is called the constant energy boundary. I mentioned it in a previous slide. Here's a constant energy boundary for 480 volts, 32 millimeters, 18 inches working distance, VCB. This energy represents 8 calories. For any particular value of arcing current, for example, let's take 10, which in this case would be 10,000 amps arcing current. In the old study, as long as I was roughly below 20 milliseconds with my protection, I was at 8 calories or better, or less. With the new 2018 study, I could be at 30 milliseconds or less and still achieve the same 8 calories. And if you look at the previous chart, 2 previous charts, 3 previous charts, 4 previous charts, that makes sense because the arcing currents are different. Actually, not so much because of that, but because the energy, difference levels are different. Notice that the red line is below the black line here. In this chart, that is shown the other way around. You have more flexibility in time because the energy per unit time is lower. This becomes a useful analytical tool when you do not have an exact value of arcing current or an exact value of voltage fault current. The problem is that for this chart, you do need the exact arcing current, and you're not going to have that unless you're doing an arc flash study. What you do know is your voltage fault current. If you plot the exact same 2 lines at voltage fault current, which is not the normal way people use that graph, it's a different way. But I'm suggesting that this transposes all of the values to voltage fault current, which you do have because you know the short circuit in your system. And if you look at your old arc flash study, that information should be available to you, or a short circuit study. You have that information, regardless whether that study was done last year or 5 years ago. If your system has not changed, physically changed, then that voltage current should still be accurate. The new 2018 arc flash calculations have not changed the way you calculate voltage fault currents in any way, shape, or form. So that value should, in fact, still be the same. So when you put the graph in terms of voltage fault current, that arcing current calculation is no longer a variable. Now you've made that data from the old study and the data from the new study comparable. So if you take all of the other variables, your gap, your working distance, your box, and hold them the same, these 2 charts are now comparable. Now notice that the line for the 2002 study is still more or less a straight line, but the graph for the 2018 incident energy per unit time varies, and it isn't more of a curve. It's got a little bit of a belly to it. Notice these 2 vertical lines. What those 2 lines represent on this graph is this region and that region. The region where the arcing current is higher than the new arcing current would be higher than the old arcing current based on comparing the 2 studies. What you know about this region here is that your protection is going to be equally fast or faster. It is not going to be slower. That also helps you now within this region between these 2 black lines. This data is comparable because you can assume time is the same, gap is the same, working distance is the same, enclosure is the same. The only thing that's different is VCB old versus VCB new, incident energy old versus incident energy new. All the other variables are essentially held steady. So now these two curves can be compared to each other. And just looking at these two, if this is what I calculated in my old study, and this is what I calculated in my new study, whatever PPE selection was good enough for this is going to be good enough for that. My PPE selection is, in fact, relative to the new arc flash study, conservative. Most people, when they select PPE, will select PPE that is higher than the actual calculated values. Most users will have PPE policies that are either 8, 25, 40, or some calorie value. They don't have 40 different levels of PPE on their facility. They will typically have 2 or 3, and typically they'll choose those values that were previously associated with hazard risk categories, or may have some other value. Whatever it is, that facility has a value of PPE that is used, typically 2, a low and a high, and that is what is used. So what is calculated for a particular piece of equipment, let us say a piece of switch or a switchboard, maybe 4, 5, 6, 7 calories. But the recommendation in the arc flash label will be use 8 calorie PPE, or the arc flash study will suggest 8 calorie PPE. The practice at that facility is 8 calorie PPE, or maybe 12. So there's a margin. There's a margin between the PPE that's going to be used, normally would be used for that task, and the old calculation for arc flash. The question would be, is that margin enough to cover the difference between the old calculation and what a new calculation would give you? And I'm suggesting that this is a method to estimate that conservatively. And here's an example of an arc flash study, and they use the term hazard risk categories, by the way, which is why you see the number 3, number 4 here. And notice here they calculate 9.5 calories, but they're using number 3. Number 3, as we all know, is 25 calories. That's quite a bit of margin. Here they calculated 11.8, I think. Again, 3. Here they calculated 31.1. They went to 4, which is 40 calories. There's a margin between this column and that column. So the question at the end of the day, is that margin enough per my decisions on acceptance or non-acceptance of risk relative to what a new arc flash calculation would yield? How do I determine that without going through the full process of a new arc flash calculation? Here is a arc flash label where the data may be described here to tell you 15.6 calories. They use class 3 arc flash hazard risk category, which, by the way, they never should have done. That's a wrong use of the term arc flash risk category, but it was a very common mistake years ago. Regardless, this means 25 calorie PPE when the exposure was actually 15.6. There's a margin of about 9 to 10 calories. Unassuming you are okay with shrinking that margin, the question is 25 calories going to be enough for the new exposure? And my suggestion is you can do an analysis. If you calculated 5, you draw your energy boundary at 5 based on the old study method. You would draw the boundary at 8, because that's the PPE you have, based on the new study method. As long as the black line is not above the green line, 8 calories is enough. It will cover you. Now, you may want some margin, because that's your policy. Then put a 4 here. That line will shift a little bit, and you may not be able to use the 8 for every situation. But The issue here is that you can use the 2002 arc flash study to essentially determine the position of this line, and some values to determine this line based on the calories of capability of the PPE that you have, that you were planning to use. And this is, by the way, bolted on IBF. Now, most of us do not have calculators to do this with, but I would submit to you that if you have a recent college kid, engineering student that recently graduated, and you give them the formulas, they should be able to create a calculator quite easily. It's actually not rocket science. For low voltage, it does get a little bit more complicated if you try to do this for medium voltage. But for low voltage, this is actually relatively straightforward to do. The third-party software will calculate these lines, but only plot them for IARC. They will not plot them for IBF. And I think if you talk to your ETAP, SKM, or whoever, and you ask them to do it, they may be able to do it. They certainly have the know-how. Another way to express this exact same information is in a table form. To go through, and I went and did this exercise, created 108 different charts, and calculated these values. The way this chart works, how do I advance? Okay, is I went and created a chart. In this case, 8 calories for the Carter lines, 5 calories for that line, and made sure that this line did not cross that line. So that gave me this value right here. The black lines represent the range of current where this analysis is valid, because I know that my protection time will be equal or faster, not slower. If I go outside of this range, there is a possibility that the arcing current is lower, and hence my protection time could change and have a bigger effect on energy than I can predict via this way. So I have to always stay within the minimum and maximum. In this table, those values are expressed here. The red line represents a VCB situation, blue line represents VCBB, green line represents HCB. I plotted this line over here, so that's where the 8 calories, excuse me, the 5 calories here came. I kind of covered it up with the green. Okay. And of course, that black line is that 52. Is this 480 volts? Yes, I'm sorry. Is this value here? That 5 is this line because that's for 480 volts HCB. So that's the HCB right here. The 5 to 84 kiloamps, which is these two lines. HCB for the black line, for the colored line, and that's where the 5 calories come from. That's where these two lines touch. So if you have a table like this, you essentially can then take any situation and say, if my previous worst energy for this task based on the 2002 study was 5 calories, and I now have decided I have an HCB situation, and I have 8 calories PPE, that's good enough. But if my previous calculation was more than 5 calories, then the PPE might not be good enough, and I need to do an actual arc flash calculation or go to the next level of PPE, which tells me I now, from 5, I now have up to 15. And if my calculation before was 15 or below, then I can use 25 calorie PPE. If my old calculation was 25 or below, I can use 40 calorie PPE. This table, by the way, is for an HRG or high resistance grounded system. Before this presentation is posted, I will add a table for solidly grounded systems. But that's the crux of the method. By understanding how your protection is going to respond to the new arcing current, by making the assumption that your gap, box, and other parameters are not changing, and the only parameter that might change is the electrode orientation, you could create values ahead of time that make sense for your facility. And now you can essentially use your 2002 arc flash study to decide whether your task is exposing your worker to more energy than the available PPE or previously selected PPE, and whether you can move forward or do something different. This should be a conservative method. It's not a complete arc flash study and should not be considered to replace an arc flash study, because this is conservative. And in fact, there are many situations here where you are still using more PPE than you need. But there should not be any situation here where you will have less PPE than you need. And this is based on the premise that wearing more PPE than you actually need, it may be undesirable. But finding out that you did not have enough PPE after the fact is not acceptable. So that's the purpose for why I created this method, and this is an explanation from that perspective. I think I'm almost ready for questions. Again, creating those plots, doing that analysis may seem difficult, but somebody that has some inclination for Excel and a little bit of inclination for math, the IEEE standard gives you all the math. In fact, let me tell you that if you know somebody that was in the ballot that actually voted on the IEEE guide when it came out for public vote, and they have the old drafts, if they have draft number 1, all the formulas in that draft were in Excel format. You just have to cut and paste into Excel, make them into variables, and voila, it works almost automatically. You don't have to figure out how to translate from math language to Excel language, because it was originally put in Excel language. You could work with your electrical system people to create the charts, but on the other hand, if you already have a model and you're going through this trouble, it may just be easier to just do an updated arc flash study, which obviously is the best thing to do. It's important to understand, again, that this is all about controlling risk, and whether the PPE that you have hanging around, the PPE you're used to using for that task, based on the new calculation method, is good enough. May not be perfect. It may still be too much. You may want more margin, and you can easily tweak the numbers in the previous chart. If that's the case, just simply lower them by 1 or 2 calories. But it allows you to look at the task, being aware that if you have an HCB or VCB situation, you have a very different situation. Take that into account and decide whether your PPE is or is not good enough. Doing the entire arc flash study by the time the task needs execution may be unreasonable, but it is, at the end of the day, the best thing to do. So eventually, you should do that. The point here is to do this with a few variables that you have access to. You can look at the electrical orientation. You have the old flash study. You know what your PPE is. You don't necessarily need to go through the full math and full decision-making process of a new arc flash study. With that, I am open to questions. Hopefully this made some sense to a few of you. And hopefully whoever it did not make sense to, I can clear it up with some answers.
All right, thanks, Marcelo. Yeah, this is an interesting topic for sure, and I know based on the audience size that has tuned in for today's event, there still are a lot of questions out there. So as you said, hopefully your slides today and your discussion helped clear things up for some folks. But it does seem we have questions that have rolled in, and I'll throw some your way now so that we can try and help clear some things up for some of the people on today's call. So the first question would be, how is it possible that the arcing time reduces when you use another calculation formula in the same short circuit situation?
Okay, sure. That's a very good question. Let me go back. It all comes down to this chart. Your fuse, circuit breaker, fancy or complicated, fancy relay, Anything that measures current reacts to this current. It does not react to this current. This current is a theoretical value of interest only to people that do short circuit calculations and people that design circuit breakers and test them in laboratories. The only value that matters is the real value that happens in the real world. 99.9% of all faults are arcing. People argue how many of them are actually ground faults or start as ground fault. But as far as arc flash calculations, the assumption is they're all three-phase and they're arcing, which means is this value of current that matters. And what you see from here is that the values calculated per the new standard are going to be higher than the values calculated per the old standard. So in the paper exercise that is an arc flash study, I am dealing with a different input into my time current curve analysis. So when I look to my time current curves, again, it doesn't matter if it's a fuse or if it's a circuit breaker. The issue is if my current is higher, notice the direction of this arrow, I am going to interrupt this curve further to the right. On a fuse, it's very clear to see because from top to bottom, a fuse is always faster. To the right I go. It's a little more complicated. In this region here, and I move a little bit to the right, I will be faster. If I'm in this region or this region, I will be the same regardless of current, but I will not be slower. So again, it goes back to the fact that current is higher, and when I plot that higher current on this graph, that value is going to be further to the right where it intersects this orange line or this black line. I am further down on the curve. This is time. My overcurrent protective device, breaker or fuse, will operate at the same speed or faster, never slower. Hopefully that was clear.
Yes, hopefully that clears that up for that individual that asked the question. And let's move on to another. This individual says, we are reperforming a study that was originally done 7 years ago. And they say, so with new IEEE 1584, do we need to change any specific parameter in the model for accurate results?
Yes. The answer to that is yes. Well, excuse me. You don't necessarily need to change them. You need to reevaluate them and see if you need to change them. The main one is this electric orientation, well, yes, that first chart. Is this thing in the bottom here? That is probably the single biggest potential change. In the old model, it was all vertical. In the new model, it could be one of these three. And these make potentially a huge difference. If you're automatically assuming VCB all the time, you have to be doing a new arc flash study bordering on a waste of time. You really need to evaluate whether it still is VCB, it still is HCB, and still is VCBB. If you have situations where your gap is significantly larger than what you originally used, that would probably bear some consideration for changing. Because if you have a much larger gap, then your arcing current could be significantly lower. And if it's significantly lower than what I said about the protective device before no longer applies, now the potential is that your protective device is actually slower. And then we go back to that chart. Your big issue is if you suddenly move from this protection here to that protection there. That's a huge difference in time, and time is a big variable. It's an important variable. Same with a fuse. If I'm moving from the right to the left, a fuse curve is pretty steep. It doesn't take an awful lot of shift in arcing current before that fuse is protecting quite a bit slower. Another consideration with fuses, but we're not going to get into now. So I would suggest to you that two variables to look at are the electrode gap orientation and pinhole. If the gap is smaller, not a big deal. But if the gap is potentially larger, that could be a big deal. The other variable you need to pay attention is enclosure size. Not a huge deal, but if you're going from very small to very large, probably something you want to take into account and put that as correctly into the new model. That's pretty much all I can say on the subject.
Okay. So sticking with the discussion here about the gap, I see a couple questions that have come in around that same topic. One says, what is the standard gap setting when doing recalculations? And then another was, investigating the right dimensions for a gap is a hard task, so what's your advice? So I think people are still looking for some guidance there on what the gap is, what it should be, how you can take that into consideration.
That's a very common subject of discussion. The IEEE guide, both the 2002 and the 2018, have a table with what they call typical gaps. And my recollection is those numbers for low voltage are 13, 25, 32, and 40. And then for medium voltage, I think for 5 kV and below, they have, I think, 104 millimeters. For above 5 kV, they say 152 millimeters or 154. Those are values that a committee, a bunch of people in a room together decided, well, those are typical. And in the old standard, I'm not sure it made that huge a difference. But in the new one, it does make a little bit of a difference. Let me give you an example. The company that I'm most familiar with makes 5 kV and 15 kV switchgear. The reality is that was the same switchgear with a different nameplate. We did not make two different lineups. It was just too cost effective to have two completely different designs, two different sets of bus bars, two different everything. We made one. We changed the bus bars. Obviously, CTs, PTs, and all that was changed according to the voltage. But the sheet metal, the copper bars, were not changed. The gaps were exactly the same. Whatever they are, they were exactly the same. Yet the table in 1584 said for 5 kV use 104, for 15 kV use 152. I would submit to you that if you were using that GE medium voltage equipment, one of those gaps was wrong. I'm not quite sure I can tell you which one of the two was wrong, but one of them was wrong because we had the same gap in all equipment, whereas the guy told you to use two different gaps. So in theory, if you want to do this correctly, you need to examine the gear and identify the actual gap. And the new model allows you to choose the exact gap. So if you decide it's 33.5 millimeters, put in 33.5. However, the one thing you can also say is, if in doubt, if you're not sure if it's 25 or 32 or 40, use 40. That's conservative. Now, you may be getting a little higher energy than you actually would like to get, but you're being conservative. If you use too small a gap, you are shifting your protection on the left of this curve. And if you're shifting, a millimeter in this area or a millimeter in here, it may not be a big issue. But if you're shifting from here to here, that's a big issue. You don't want to do that. So it's more important to be conservative in arcing current, which means you want a low arcing current. So if you're going to be potentially operating in this portion of the curve, you're going to be operating in this portion of the curve and handle it appropriately. Shift your short time setting to the left, do whatever you need to do. But you don't want to think you're here and then find out, oops, I'm actually here. That would not be good. So when you use a larger gap, you're shifting to the left. You're being conservative. You also get more energy per unit time. You're being conservative with energy. So in short, measure the gap if you can. If you cannot, guess high, don't guess low. That's it.
Okay. So sticking with the electrode and configuration here, I've got a couple questions that go together somewhat. So the first one says, in a cubicle, you have more than one situation, and they reference VCB, HCB, and VCBB. So what do you choose if you've got multiple configurations in a single cubicle?
Okay, that is definitely possible. First, see if you can discard any of those configurations. It does not necessarily matter the directions of wires or bus bars. What matters is the direction of the bus bar that's feeding the arc, where the power is coming from, not where the power is going to. So if I look at a box, let's assume I got horizontal bus bars coming straight at me. They take a 90-degree turn and go out the top of the gear. Now I look at this. Well, I have vertical bus bars and I have horizontal bus bars. Horizontal is typically worse than vertical, so my assumption would be to go horizontal. But then I look at where is my generator, where is my source of power or transformer, whatever it is. If the generator and the source are at the top, i.e. coming down those bars, then making a right turn and going away from me, that is not a horizontal exposure, that's a vertical exposure. The power is coming from the top. On the other hand, if the generator is on the other side of the switchgear and the power is coming down those horizontal cables, taking a right turn and then going up to whatever my load is on the top of the gear, that is a horizontal exposure. The vertical doesn't matter. The power doesn't come from the vertical, the power comes from the horizontal. So that's one way that you would potentially discard the multiple potential exposures within one enclosure. If you still have multiple exposure modes where power could be coming from in the same enclosure, now you need to look at the fact that horizontal, vertical, all else being the same, affects both incident energy and arcing current. So for example, if I have VCB and VCBB, you probably need to look at both, because the VCBB will give you much lower arcing current, which means, again, you could be in the region where your protection on that breaker goes from horizontal to that slow purchase up high in the curve. And yeah, VCB per unit time is less energy, but your time is just multiplied by a factor of 10. On VCBB, gives you more energy per unit time, but typically gives you a much higher arcing current. So your protection is going to be operating further to the right on the curve. So even though you have more, it's a bigger explosion, it lasts so much less time that the net effect is it's less exposure. So you may be presented with the unlucky situation. You kind of need to analyze more than one, make sure your protection can deal with the low current of one and with the high energy of the other. So you may need to do your analysis essentially twice. There is no clear answer that one is always more dangerous than the other. HCB is always more dangerous than VCB. That you can pretty much state clearly. But when you have VCBB in the mix, it kind of makes it difficult because of the much higher arcing current. Hopefully that was clear as mud.
Well, I think the good thing is I believe you answered the other question as well, so we can move on. Looks like we have time for maybe one last question here. This one is, I saw another one in the list that was similar to this. Any comments about the 240 volt, 125 kVA rule?
Why am I getting all the hard questions? That's another hotly debated subject. I don't know that there's a clear answer to this. The IEEE standard is a guide for calculations. It is not a guide for risk assessment. It is not a safety standard. It is a guide. This is the science. This is what we know about the science. And the guide is, and I don't recall the exact words, and I don't have the text in front of me, but attempting to paraphrase, essentially says the formulas are good to these particular values. And it uses, forgot the exact numbers, I think it's 2,000 amps, 240 volts. It took the kVA discussion out of the picture and now talks about amps and volts. And it basically tells you the calculations formulas are good to this based on a understanding or perception that you can have an arc at these low power situations. How often? Whether they will snuff itself out, whether it will not, it makes no statement about that. There is no discussions of probabilities in this document. They say the formula works to this end. 70E has its own discussions on the subject, I believe. You would have to read the exact text. And again, I don't have it in front of me, and I don't want to attempt to paraphrase it. But at some point, we all kind of think common sense. Power is too low, gaps are too big, probability of the arc sustaining is low. The decision, however, we need to make from the risk control perspective, is it low or is it zero, close to zero? Because if it's low but not quite zero, then there is a risk. And if you determine that there is a risk, then you need, per standard industrial hazard risk assessment, you need PPE. And the PPE is not dependent on probability of the event. It's dependent on the severity of the event. So once you determine that there is a possibility of an arc, you go to the IEEE formulas, they give you a potential severity. That's what you need to deal with. Anything else, you are making the decision that you know the risk and the risk is low enough to ignore. That is not a decision, and luckily I can make for you. What's in the text is what's in the text. That is, at the end of the day, a decision you need to make. But be clear, you make a decision on probability. If it's not zero, you need PPE. If you need PPE, then you go to the calculation of severity to decide on the level of PPE. You don't cut the PPE in half because the probability is low. You don't do that. At least that's the traditional risk assessment and risk control procedure. That's that.
All right. Well, Marcelo, I appreciate you addressing those difficult questions. Yeah, our audience is pretty diverse and pretty knowledgeable, so I'm glad they put you to the test a little bit there. But thanks for answering those. Before we sign off, I'd like to thank our sponsor for making today's event possible, ABB. As you can see on the screen, there's a customer solutions showcase that they're got a little bit of information on the screen for you to take a look at here. I'd like to remind everybody that this webcast, an on-demand version, will be made available on the EC&M website. It'll be up for a year. The link to that recording will be sent to you via email, probably in the next 24 hours. And thanks so much for attending, everyone. Have a safe remainder of the day. And Marcelo, thanks again for a great presentation.
You're welcome.